Okay, this meeting is being recorded. So yes, there is water on the moon. And as I said, this is our team of people from Polychromics, the company I was involved with for many years, that built the equipment I'm going to be talking about. And Dave Day was the leader of the Polychromics team that worked on this. This picture was from more than a week ago. I used to have dark hair. This was taken on a happy day in the company. We were a startup company. We just gotten our new Polychromic shirts with the logo on it. So we were all very happy. The NASA team that I'll be talking about, led by Tony Colaprete, was quite large. And you'll get a sense of the size of that effort. Okay, so what prompted all this? The old news. On October 26th of this year, I read in the Washington Post that a pair of studies confirmed that there's water on the moon. Well, we already knew that. And the article was nice, but the water on the moon bit was old news. Now, the thing is that this article didn't mention the LCROSS mission, which is the mission I'm going to be talking about today. And so I kind of got my back up a little bit and said, I'm going to put the record straight. And as a result of that, I decided to create this talk, which I did with David's help. So the real deal is that water on the moon was first confirmed by the NASA LCROSS mission in October of 2009. And what I'm going to do today is walk us through the mission, why our equipment from a little tiny company called Polychromics was selected, and then walk you through the mission and then have NASA explain the results to you. In terms of background, it was indeed known from a lunar orbiter, Chandrayaan-1, that there were molecular signatures of water on the moon. And by molecular signatures, I mean spectroscopic evidence for hydroxyl groups, OH, which is part of H2O. And the hydroxyl group could have been absorbed from vapor that was originally on the moon, or it could have come from the Earth, or it could have come from a comet, or it could have come from no one knows where. But the point is, there was evidence of hydroxyl groups on the surface, and it could only see the surface. And the LCROSS mission was designed to look under the surface. I'm going to take a small diversion to tell you about a smart first grader. Shortly after the LCROSS results were announced, and this would have been in the spring of 2010, I gave a science talk to my granddaughter's first grade class because she had come home announcing with great pride that there was no water on the moon. And I said, oh, yes, there really is water on the moon. She said, no, my teacher said there's no water on the moon. So I called the teacher and I said, actually, there is water on the moon. We found it. We being an extended we, meaning NASA found it using our gear. And so she invited me to come talk to the class about it. I gave a science talk. And there was a very smart girl in the room named Charlotte. She's now a 10th grader at Brookline High. And she said, maybe there's water frozen under the sand. Well, she's right. And that's what the LCROSS mission was looking at, for water under the sand. The idea was this. The mission began in 2006. The notion is that you take a rocket casing, once it's used up, it has no use at all, and just throw it at the moon and let it crash into the moon and kick up a pile of dirt, and then send an instrument package behind it that would make measurements of what was kicked up to see if there was water. It's a look under the sand, just like Charlotte said. It's what we call a do once experiment, because after the instrument package has made its measurements, it also crashes into the moon. So this is it. Schematically, rocket casing goes off and hits and makes a big flash. The big flash produces heat and light and dirt. And if there's ice in the dirt, it evaporates and produces water vapor. And then the instrument package comes and looks for it. So here's what NASA expected to happen. right away, when impact of the rocket casing occurred, there would be a bright flash of light and a plume of material and a blanket of lighter material thrown out to the side. Within a time scale of minutes, and with a distance horizontal scale of 10 kilometers, they expected a big explosive cloud full of dirt and subliming water vapor from the ice crystals, if there were any. And it's this portion of the impact that we're going to focus on, because that's when our instruments were used to look at the water vapor in this cloud backlit from the warmth of the impact crater. That's the notion. And then over a longer time scale, when the water has evaporated well outside the area of, this is the crater Cabeus, which is near a pole and is in shadow most of the time. Solar UV light hitting water tears it apart and produces hydroxyl radicals, which give off a special color of light and allow a parallel and confirming identification of water vapor that might have happened from our instruments diving through this cloud. Okay. The crater Cabeus was chosen because it had a very shallow rim, but it's in shadow all the time at the bottom. But when the dirt is kicked up, it would get up above the rim and maybe be visible from the Earth. That was the notion. Well, I'm not sure it was ever visible from the Earth, but it was certainly visible to our instruments. So let me say a little bit about measuring things with light. We are aware that there's an electromagnetic spectrum with visible light, and at shorter wavelengths, there's ultraviolet light, and at longer wavelengths, there's infrared light. The infrared is broken up into regions near, mid, far, and our instruments are looking in this portion. The notion is that chemical species absorb light at characteristic wavelengths. And by observing the wavelengths pattern of absorbed light, you can determine what the chemicals must be around. That's called spectroscopy. Now, the instrument package included regular cameras, both visible light, mid-infrared and near-infrared, just looking. And then it included spectrometers to do chemical analysis, near-infrared, and then one also working in the visible UV that was looking for the hydroxyl signature. Our company, Polychromics, supplied the near-infrared spectrometers. Now, to qualify for a mission like that, you have a long list of things you have to be able to meet. The spectrometer has to be small, less than 2 liters. So think about less than a half gallon of milk, total everything. Lightweight, less than 2 pounds, meaning lighter than a half gallon of milk by quite a lot. It has to be energy efficient. The total energy budget is 3 watts. And it has to be sensitive enough, of course, to detect the water, and it has to be fast enough because, after all, it's going to crash into the moon. So it's got to do the measurement on the fly. And then it has to be operable in a hostile aerospace environment with cosmic rays and other things, vacuum, cold, dark, that kind of business. It has to be reliable to NASA standards. And I will tell you that Dave and the rest of the team and I got a very great appreciation for what that means. These guys are good. They know what they're doing. They're competent. They're capable. It's nice to know that there are people in the government who really do know what they're doing. Now, it turns out that the NASA version is just a slightly ruggedized version of an existing Polychromics product. Now, this is not the Polychromics version. This is the version that was made by Thermo Fisher after they bought our company. But the notion is, imagine something that looks a little bit like an electric drill. It has a light in this end. You hold it up against something, like up against this cloth. You pull the trigger, and on the screen, it tells you whether it's cotton or polyester, wool, linen, whatever. Or you hold it up to a bag of white powder, and it tells you whether it's talcum powder or heroin, or I could go on and on. It's a materials analysis instrument, portable, lightweight, low power, compact, not so heavy, people can carry it around. So we already had the basis for meeting the NASA requirement, because this handheld instrument combined many things, displays and a casing and a trigger and a battery inside and an optics module and circuit boards and a light source and everything. Focus on this. This is the optics module. That's the piece that was small enough and light enough and low enough in power that it could be adapted to the requirements of the NASA program. The rest of it was not relevant. Okay. Now I want to tell you how this little tiny spectrometer works. It works because of a specific piece of technology that we developed, and that was the basis for founding the company in the first place. It's called a diffractive MEMS chip. It has a fancy name, a polychromator, but we don't need the fancy name. The way this thing works is the following. Light from the thing you're looking at is brought onto a diffraction grating. Now you're all familiar with how a prism breaks up light into its colors. Well, a diffraction grating does the same thing. Now I've pictured these colors as red, green, and blue, but you have to imagine that they're all in the infrared. So the red represents the longer wavelengths and the blue represents the shorter wavelengths. And they're brought to focus on the surface of this diffractive MEMS chip, which does something miraculous. What it does is it either, depending on how we control it, it either reflects the light from this color back out to an output fiber to a detector, or it diffracts it away. So this is like a really fancy wavelength dependent light switch. It switches some wavelengths so they're diffracted and other wavelengths so they're reflected. And that's what it does. And thought you might like to look at how it's made. Think of it as a bunch of really long, narrow piano keys. Now this schematic shows short piano keys, but the actual piano keys are very long, 50 times longer than they are wide. And they're built up on a superstructure with a beam underneath that when I put a voltage on it, that lower beam bends and the piano key can go up and down. It stays parallel to the surface, but it rides up and down like this. So if I have all of these at the same level, it's a mirror and it reflects the light back. And if I depress every other one to the right distance, it diffracts the light away and no light goes back. It all goes off to an absorber. So this is a light switch. And the way, I'll show you some photos. This is the cross section and this is the actual chip. Now the dimension here is 42 micrometers. That's about the width of a very nice, fine human hair. So if I laid a human hair down on this picture, it would pretty much cover everything. There's the lower beam, there's the upper beam. This is my Apple Watch telling me I have a phone call, which I'm ignoring. There are interconnects in a structure. This is what the package device looks like. And the little beam, the little piano keys are running this direction. And the whole thing is, it's an inch. It's small. This is just another expanded structure. And now the scale on the right here is 8.5 micrometers. And you can see that it's really a beautifully sculpted structure with lots of detail on the micrometer scale. This is very small. It's made with microelectronic technology. Okay. So to meet the specifications, in addition to size, weight, ruggedness, power consumption, all of which we could do, the measurement had to be sensitive, yeah, calibrated, yeah, and accurate, yeah. It also had to be fast. The entire measurement time is only a few minutes from the rocket casing crashes till the instrument package crashes. And you got to do everything. You got to make the measurements, analyze the data, and pipe the result out to I think it went to the lunar rover orbiter before it went back to Earth. I'm not sure about that, but I think that's where the data path. There was another orbiter going around at the same time. The point is, It took 100 different settings of up, down, different parts of the chip up, different parts of the chip down. You made 100 different settings and you collect how much light comes from each setting as a time record. And then in a very short and easy calculation, boom, you have a spectrum. That's how it works. But the little silicon beams are very lightweight and they're very small and they're very easy to move. They move fast. So they move to their new positions in thousandths of a second, in milliseconds. So a complete spectrum with 100 different settings only takes 1 second, including the conversion to a spectrum. So you can take one spectrum, then you can take another one and another one and another one and average them together to get better signal. Okay. So Polychromics with Dave's team provided 2 identical instruments to NASA. They actually provided 3. 2 of them were for flight, and 1 of them was for NASA to beat on and try to destroy. Now, these instruments were delivered in May of 2007. So that's a year after the program started, but notice it's still 2 years before launch. They had to go through space qualification, shock testing, no problem. Testing in ultra cold temperatures, no problem. Testing in vacuum, problem. That little chip I showed you has a window on it, and the seal from the between the window and that little case was leaking. Well, why do you care, you might ask? It's a good question. If the gas that's inside that chip leaks out, here's what happens. You move the piano keys and they just vibrate because there's nothing to slow the vibration down. You need the gas inside the case to prevent the thing from just vibrating. It's supposed to just move and stop. That's called the gas damping. Well, we had to go and improve the seal, which we did. And then we had to prove to NASA that the vibration of the structure after you put voltage on it was a valid proof that the device was not leaking. And to the extent that I contributed to the mission, my one contribution to the mission was I gave them the formula for that calculation. Other than that, it was the engineering team that did everything. But we did survive that. And so that was the first. Okay, there are more to come. Now we're looking at the assembly of the spacecraft. Over here are the 2 spectrometers side by side. One of them is going to be looking down at the moon. The other one's going to be looking at the sun. These are the windows where the light comes in. And this is the other spectrometer, the one that operates in the visible and the ultraviolet. And these are very careful, clean people putting things together. And now these are more careful, clean people putting more stuff together. I want to give you the impression that this is a box within a box within a box within a box within a rocket. That's what we're making here. But our boxes are essential. If they're not there, they can't see the water. But it's a pretty big deal. This was at Cape Canaveral. And now you see these are the bottom half of people bolting or making connections between the instrument module and the rest of the spacecraft. This says LRO, that's the Lunar Reconnaissance Orbiter, which is the satellite. And then this is the LCROSS instrument package inside here. This was the, to get ready to put it on top of a rocket. Now, where does it go in the rocket? Well, the rocket is mostly engine, lots of pieces of engine. But then up in the payload part, there were 2 things. This LRO that orbits the moon, and then the LCROSS, which is our instrument package. And it sits just on top of various chunks of stuff. The Centaur upper stage. This is the guy that's going to crash into the moon. Okay, are we ready? It's time to launch. And this is where the spectrometers are living while this launch is going on. And Dave, I believe you were at the launch. Is that correct? Yeah, Dave was at the launch. He got to witness this. He'll be able to tell you how his ears survived the noise. It was quite exciting. June 18th, 2009. Notice that's 2 years after the delivery of the spectrometers to NASA. And within 2 days, we had heard that the spectrometers were functional. They worked. They survived the shock. Nothing shook loose during the vibration of the launch. And in early August, NASA pointed one of the spectrometers at Earth to see if it could detect water on Earth. We have plenty of water on Earth. We have oceans of it. But could we see it from space? Another, yes. This is the Earth, and that green circle is what's called the field of view of the instrument looking back at the Earth. It's looking at a portion that has plenty of water, and lo and behold, we see the water. Now, how do I know we see the water? Well, there's not much light coming back to the spacecraft from the region where water absorbs to the wavelength region where water absorbs light. That's the key notion. If water were not there, there would be a lot more light coming back from Earth at this position of the spectrum or at this position of the spectrum. And you can also see different compounds at different wavelengths, carbon dioxide, methane, heavy water, and so on. Okay, so good. But then we had to wait because the spacecraft has to go to the moon, get into the correct position, release the Lunar Rover Reconnaissance Orbiter, get the rocket casing and instrument package positioned exactly in the right place so that when they let go, it would hit in the dark part of Cabrias, the crater. And so we just have to wait. And I will say that this was as nervous a time for me as any of it, because there's nothing you can do. We got a considerable appreciation of the tension that goes on during these space missions. You've all seen photographs of these rooms with people lined up at terminals looking at screens and waiting and waiting and waiting. Well, we got a small sense of that waiting for news that our spectrometers had woken up after this month in the cold and the dark. Well, I did wake up, and it brought me to tears. I was overwhelmed. I didn't know if we were going to see water, but at least we had delivered the goods to the moon and it was working. Okay, what's next? Impact time, October 9th, a day that will live in my memory for a long time. The Centaur rocket casing was sent on its mission and the instrument package was following behind it with a hope and a prayer. Well, it hit, the rocket casing hit, and there was a flash, immediately detectable. It's hard to see, it's right there. And this is an expanded view, and this is a much expanded view. So there was a flash, just like there was supposed to be a flash. And boy, did our spectrometer see it. Boom. The light from it hit our spectrometer, and the spectrometer said, there's light at the bottom of this crater. Okay, good. What's next? There was a plume of dirt kicked up. That was the next thing. Now, this is the plume, and this is an expanded view of the plume. And notice it's about 10 kilometers across, which was what they had hoped for. These guys were smart. Smart. And now, instead of me telling you what they saw, I thought it would be more fun to have you listen to NASA, Tony Colpreet from NASA, tell you what he saw.
Now, without further ado, I'd like to turn it over to those that made it happen. Tony?
Thank you, Pete. Thank you. It's good to be here again. As Pete mentioned, about 1 month ago, we made an impact, and we saw some squiggly lines, and we've been working about 28 hours a day, a large team to understand what those mean. And so I'm here today to tell you that indeed, yes, we found water. And we didn't find just a little bit, we found a significant amount. If you remember, about a month ago, we were talking about teaspoons going to glasses over football fields. Well, now I can say today that in the 20 to 30 meter crater Elcross made, we found maybe about a dozen of these 2-gallon buckets worth of water. So this is initial results, it's preliminary. You're going to hear how we came to this conclusion today. I'm going to walk you through it. And it's probably a lower bound on the total amount of water we've seen here. and there's a whole lot more beyond the water. So that's the exciting part in my mind, is it's not only about the water now. There's actually a lot more here that we're going to be talking about in the months ahead, looking at the LCROSS data. So it's a very exciting time for us. The science team has been working exceedingly hard. I'm very honored to be a part of such an awesome group of people who've really been working pretty much nonstop for the last month to look into the data. And you'll understand why it's taken us a long time to come to some of the conclusions here in a minute. So what I'd like to do is bring us back a month ago. I probably was a little more tired than I am now then. But and pick up where we left off with the curtain, what we saw with the ejecta cloud, and then just step you through some of the points of analysis that we did to come to the conclusion that I just asserted. So with that, let's go to the first slide. The first slide will show a visible camera image of the ejected cloud. This is an image that was about 20 seconds after impact. We saw a nice plume rise. It was, in this particular image, the inset shows to the lower left the plume. It was about 10 to 12 kilometers across at this point. This camera, we weren't very hopeful of actually seeing the ejected cloud, so we were quite pleased that we saw it. It was a nice large plume that came up. In the next slide, it shows the approximate field of view of the instruments I'm going to talk about that did this water detection I just described. The red circle there shows a 1 degree field of view at just shortly after impact for our instruments. And what's important about this is that field of view, that red circle, is almost completely filled with ejecta cloud. That's important because that is filling the instruments with the signal, with the light, the information we needed to understand what was in the ejecta cloud. So it worked really well. We picked the time, the fields of view, and everything else like we had hoped, and it worked. We actually filled the instrument with signal, which was really important. The next slide shows some of my favorite bits of data from the mission. At the very end, we turned one of our near-infrared cameras to a long exposure, and as screamed down into Cabeus. Dip below the bright rims, what we saw was a floor Cabeus revealed for the first time in 1 or 2 billion years. We have not seen the floor of Cabeus ever, of course. It's in permanent shadow. But these near-infrared cameras were able to image light that was radiating from the walls, scattering in from the rims of the craters and whatnot, and revealed what you see here. And eventually, what we could see, both in our thermal cameras, we could pick up the heat from the impact, and also this image, we could register them together. We could see the crater, the brand new fresh crater the Centaur had just made in this field of view. The arrow's pointing to it. What you see here are those bright hills. Those are nice sloping hills pocketed with smaller craters, some larger craters here. The scale on this image is a couple kilometers across or so. It's about 4 kilometers above the surface when we took this image. And you can see our crater down there with the arrow pointed. And the next image shows that crater zoomed in inset. We hit into a nice level flat plane, which is exactly what we wanted. It is one of the coldest places in Cabeus. The Diviner instrument saw our impact crater as well on the LRO spacecraft and measured the temperature in the region where we impacted at about minus 230 degrees, 220 degrees below 0 Celsius, so very, very cold. And you can see in that inset the crater we made. The dark area in the center is the crater. The brighter area is ejecta that has been spilled out across. The crater we made was 20 to 30 meters across, and the ejecta, the bright area there, is approximately 60 to 80 meters. We have information that indicates that the ejecta blanket actually went much broader, out to several hundred meters outwards, really affecting the area. This is a nice, large crater. What we expected in the 20 to 30 meter class means we hit in relatively unconsolidated, weak material. And that's what resulted in the ejecta plume that you saw in the previous slide. So what did we see from the instruments that detected water? And that's what I'm going to talk about next. Next slide shows the 2 instruments that I'm going to describe in detail to you. The instruments that we're going to talk about are spectrometers. The spectrometers measure colors of wavelengths. And those colors are affected by various compositions from various compounds, for example, water or carbon dioxide or whatever. Each compound will affect those lights differently. We have two instruments that we used on this mission to look at that plume: an ultraviolet invisible spectrometer, the one indicated there on the lower left, and near-infrared spectrometers. We had two near-infrared spectrometers, one looking down and one looking to the side at the sun. Today I'm just going to talk about the two that were looking down, because those are the two we focused on to provide the results I'm describing today. The next slide then shows some of the near-infrared spectrometer results. Unfortunately, spectrometers often just give squiggly lines, not pretty pictures. However, these squiggly lines are really important because they are, as I mentioned, the change in these colors and the changes in those lines really tell us what we're seeing in that cloud. What I have here is a plot of brightness against color or wavelength. And the black line with the little hash marks, the vertical hash marks, is the data, the observation. This is an average of about 20 to 60 seconds after impact. We've averaged a number of instrument scans together. The black vertical hash marks are uncertainty bars, or error bars in the measurement. Why I show those is to show that these measurements, these dips you see in the line, are real. They're not just noise, they're very real. And what you would expect to see if you're just looking at bright, colorless gray dust of ejecta is shown on the next slide. This red line shows a continuum, a black body, what we call black body continuum, something hot. If this is warm dust coming up about, say, 400 or 500 degrees Celsius, you'd see this nice red smooth line all the way across like you see here. That's not what the data sees. Data it kind of comes up and meets that line, but then it has all these notches taken out of it. And each of those notches is a compound, some kind of material absorbing infrared light, near-infrared light. So the first thing we did was, well, let's put in some water and see what happens when you put water into that model, that red line. And the next slide shows that. And we get a good fit in two regions. The two regions are indicated by the yellow. Those are the water bands, water vapor and ice bands. There's actually a third to the left that I don't show here at about 1.27 microns, shorter wavelengths to the left, that actually shows this as well. We got good fits. This was a unique fit, meaning we could not put other compounds in here and generate this same fit. So we were really excited. It was a pretty tight fit within the error bars for water vapor and ice. Now, all those other bands and bumps there are of interest too, and we've been studying those. And I don't want to say too much beyond what I've already said on those bumps and wiggles, except the next slide shows that we can actually fit them all pretty well with a variety of different compounds. And that's when I said this goes beyond the water. It really does. There's a lot of stuff that came out of there, and you're going to hear about this a little bit more as we discuss this on the panel, but there was a lot of stuff that came up out of the floor of Cabeus, not just water that we saw.
I'm going to stop at that point. The briefing goes on to talk about the results from the ultraviolet visible, where they saw confirming evidence of the presence of water from the emission of excited hydroxyl groups that were produced by ultraviolet light hitting the water vapor that had evaporated out. But the real point was actually at the very beginning of that presentation. We found water, and not just small amounts of water, but buckets of water. So at this point, I'm happy to end my presentation and invite discussion